Hi there, just a quick wee video just now about some of the terms that we're going to come across just in the first few lessons of higher chemistry. We're starting looking at the periodic table, focusing in particular on the first 20 elements, and we're looking at their bonding and their structure. Now, bonding, if you remember from previously, there are different types of bonding. There's covalent bonding, ionic bonding, and metallic bonding. Okay, so that's what we mean by bonding, how they're being stuck together. The structure is how the atoms are arranged. So if you remember, in covalent bonding, you get things being held together in little clusters that we call molecules, or in huge big arrays that we call networks. So we get different types of structure. We've got molecules, networks. We've also got lattices. If you remember, ionic things that exist as lattices, and metals exist as lattices as well. Okay, so that's bonding and structure. We're going to this lesson look particularly at the noble gases, and they have got their own structure, their own arrangement, because they don't exist as molecules, they don't exist as networks, they just are by themselves. We say they are monatomic. So there's no bonding in the noble gases, but there is the structure we describe as them having a monatomic structure. So what we're going to do is have a wee look at noble gases and look at their boiling points and dig a little deeper and sort of establish a few wee principles from this. So we've got our boiling points of our noble gases here on this page here. The helium, that has got the lowest boiling point. Neon is a bit higher, argon's a bit higher. So as we're going down the group, we can see the boiling point is increasing. So what this is saying is if you've got really cold samples of each of these, like absolute zero at minus whatever it is, 273, if you warmed helium up a little bit, it would soon turn into a gas. You'd have to warm neon up a bit more before it would turn into a gas. So now in higher chemistry, we're going to see if we can kind of account for this difference. And it all comes down, comes back really to this model that we saw way back in S1 science. This idea of solids, liquids and gases, where the solids are all held together. They're held in place, they're not able to move. Whereas the liquids, they've got a degree of movement. They're still attached, they're still stuck, but they can slide over each other. Gases, we say they're free to move really. Now, we're going to be particularly focusing on this, the boiling stage, when we're turning a liquid into gas. Let's just think of what's happening there. We've got these particles which are still kind of attached to each other by little forces. Okay, that was what we called our that's what we call our van der Waals forces, or intermolecular forces at National 5. They're being overcome because, think about it, we're giving them heat, we're giving them more energy, so they're able to move around more and eventually have enough energy to overcome the forces of attraction between them, and then that's them turning into a gas. So if we think of neon as a fairly small noble gas, it has just got 10 electrons. We account for what's going on here when we've got liquid neon turning into gas phase neon. If we think about a neon atom, it has got 10 protons. It's atomic number 10, so that means it's got 10 electrons. Now the protons and neutrons we're actually not really very interested in just now, because they are stuck right in the middle of the atom, okay, in the nucleus. The electrons though, they're flying around, so there are 10 electrons, which we could just draw 5, 6, 7, 8, 9, 10. 10 electrons just whizzing around at random. They're really light, they're really mobile compared to the big chunky things right in the middle. But if we compare them, if we think rather of just a moment in time, okay, there's no reason why you wouldn't get, for a moment in time, more electrons at one end of the atom than the other. So this wee uneven distribution of charge, we've got a special name that we give that. Uneven distribution of charge we call a dipole. But because it is just there for a wee moment in time, you know, a fraction of a second, really just these electrons are whizzing around all over the place, we call it's very much a temporary dipole. So for a moment in time, you might get a few more electrons at one end than the other end, making this end, if you think about it, there's all this sort of electron density at this end. That end of the atom, just for a moment in time, is going to be partially negative with all these extra negative electrons just whizzing around there. So we've got a special way of sort of showing that with the lowercase Greek letter d. Okay, so delta negative means partially negative. So that means this end, if it's got electrons kind of withdrawn from that, this end is partially positive. Okay, not like an ion with a full-on positive charge and negative charge, but just partially positive, partially negative. Okay, so that's our neon atom. There's no reason to say that for a moment in time you wouldn't get this happening. But if we just extend that a little bit and think about how that would be affecting a neighbouring atom, okay? So that's a sort of neon next door to it. What effect will all this sort of area of negative charge have? That's going to push the wee light mobile electrons away to this end of the atom. So we could draw in our 10 electrons, but again have them kind of more over to one side than the other. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we've got again more electrons towards this side than this side. So we can write again our special way, delta negative, delta positive. Okay, so again, this is a dipole. It's an uneven distribution of charge. So again, a dipole. But another fancy word, this dipole here in this atom was set up or induced by the dipole in this atom. So we call this an induced dipole. Induced dipole. So if you just have a wee think then, we know a wee scientific principle, again, right back from first year or thereabouts, opposite charges attract. So if you've got an atom that's partially negative at one end and another atom that's partially positive there, you're going to get an attraction between these two. And I'm just drawing that with a wee green dotted line. That's to show there's an attraction there. And we've got, that's what we call our intermolecular force. We've got a special name for this one. This is called, again, here's the next new term, a London dispersion force. It's got nothing to do with the place London. It's named after the guy who sort of discovered them. So it's quite a weak force. We'll find out as we go on there are actually 3 versions of intermolecular forces. And the London dispersion force here, that's just the weakest of those 3. So where were we going with this though? If we think back, we were talking about the noble gases and why we see a difference in the boiling point. So how does this explain it? Well, we were just saying there neon is quite a small noble gas. It's got just 10 electrons to be distributed. So if you think about if you have an uneven distribution, if you've got a dipole in one neon, it can only be so big. But if we compare that to a bigger, chunkier atom, I've got on the next page a similar sort of drawing, but for krypton. Krypton's got 36 electrons in it. So if you imagine these 36 electrons, I've drawn them evenly distributed here. For a moment in time, you might get a whole pile at one end, way more than at the other end. So you've got really quite a significant uneven distribution in charge. You've got really quite a significant dipole in this atom. So that's going to set up, again, quite a considerable dipole in this atom. This is going to induce a dipole in that atom. But because there are so many more electrons here, there's a much greater electron density. It's just scaling everything up. So compare that to our wee neon picture here. Just a little weak London dispersion force. But when there's a load more electrons here, in krypton, which is further down the group, you get a much stronger London dispersion force. So how does that relate to boiling point? Well, if you think about what we were saying way back here in S1, what do you have to do to turn a liquid into a gas? You've got to give the particles enough heat to overcome the force of attraction between them. Okay, so if you warm them up, you're giving them heat, energy, and they're able to separate That's enough energy to overcome the force of attraction. So as we go down the group then, more electrons, more electrons, more electrons, more electrons, you're going to get stronger London dispersion forces between these atoms. So therefore, you're going to have to put in more heat to boil these substances. Okay, so hopefully that was helpful to you. And all the best in working through lesson 2.